the general equation for a polynomial of degree n looks complicated at first. Let's take a look at it. I'll write it out and then we'll explain the component parts, give you an example, something that you're probably a little more familiar with. But in general, a polynomial looks like this, where we have the coefficients and then the variable to the power. And so you're going to see something like this. Those are subscripts: n, a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, a to the n minus 2. So n is called the degree of the polynomial. So if you go with something that, like I said, that you'd be familiar with, if we went with 3x cubed plus 4x squared minus 5x minus 9. So this would be the leading coefficient, a of n, or 3. So it's a third degree polynomial because the term of highest degree is a 3. And so you can see that the degree of each x term decreases. So it goes 3, 2, 1, and it ends up with a first degree and then the constant at the end. So the last term, a sub 0, the constant in the polynomial in this case is 9. And so this is for any polynomial of any degree. Like if it was a 5th degree polynomial, then we'd start out with the first coefficient, which would go with x to the 5th, and then you go x to the 4th, and x to the cube, and then all the way down to x to the first power, and then you'd end up with the constant term. So in terms of some of the vocabulary, some of the words that we use to describe this, these are called the coefficients. You've heard that before. This is the constant term for the polynomial. Regardless of the value of x, we'll always have a 9 there at the end. This first coefficient, that's referred to as the leading coefficient. And then this highest power of the polynomial, that's what's referred to as the degree of the polynomial, or the power of the polynomial. Okay? This entire term up here, this is the leading term, leading coefficient, power, or the degree of the polynomial. Okay? Polynomials all have similar graphs. They're all what we call smooth graphs. They don't have gaps. They don't have corners. They're all smooth, and there's no break in the graph. What we've been talking about up until now with linear equations and with quadratics, those are examples of polynomials. The parabola, those are all smooth curved. You'll notice that we talked about absolute value function. That's not an example of a polynomial. The graph of that absolute value function is certainly not smooth. It has a nice sharp corner there. That's not one of the characteristics of the graph of a polynomial. So one of the things that we did back in chapter 2 is we talked about some standard equations, some standard functions that you need to be familiar with. And we've already seen the equations. For example, the simplest polynomial is p of x equals x, and that's just a straight line. Y equals mx plus b. The slope here is 1. The b is 0. Or if we go with the polynomial x squared, you've seen that one before. The polynomial p of x equals x cubed. You be familiar with that one. Looks like this, right? So polynomials is something that you've seen before. It's just now that we're going to expand into higher degrees of polynomials. Something else that we've also seen before is this idea of transformations. We looked at transformations with quadratics, and we know you can shift right, left, up, down. You can reflect it around the x-axis or the y-axis. You can also put a coefficient out front and stretch it. Let's just look at an example of the transformation with a higher degree polynomial. For example, let's go with the polynomial p of x equals